Okay, so today we are going to look at empirical and molecular formulas. So we just finished off with reviewing percent composition, and we are going to tie this into solving for an empirical and molecular formula. Okay? So empirical formula is the lowest whole number ratio of an atom in a compound, whereas molecular formula is the true number of atoms of each element within that formula of a compound. So make sure you have these definitions down. Empirical is the simplest form, molecular is the true number or true value of atoms. So if I was looking at examples, molecular formula should be the simplest version of, or not the simplest version, should be a variation of empirical formula where we could divide all the subscripts and pull it out to be on the outside of our actual empirical formula. So for example, I have the molecular formula of C6H6. This can all be divided by 6. So if I pull that 6 out here, CH would actually be the empirical formula in this. So several compounds can have the same empirical formula but have different molecular formulas. So notice over here, formulas for ionic compounds are always empirical because remember we use the swap and drop method for ionic compounds. So it automatically gives the simplest subscript values. So we can't simplify it any further. But when we are looking at molecular compounds or covalent compounds, they might be empirical, so they may be in their lowest form, or they can be simplified even further. So if we were looking at H2O, our covalent compound, it is already empirical or in its simplest form. Whereas glucose, another covalent compound, its molecular formula is C6H12O6, but it can be divided by 6 and be simplified. C12H22O11, although these two can be divided by 2, this one cannot, so it is already in its simplest form. So what we are doing is we are taking a specific amount of a substance and we are pulling it together to derive formulas like this. We're used to swapping and dropping or being given the molecular formula. Now we are going to solve for the formulas ourselves. So first we start with empirical formula because we need empirical to solve for molecular formulas. First we are going to base all calculations on 100 grams of a compound, determine the moles of each element in the 100 grams of the compound. Then we're going to divide each value of moles by the smallest of the values, and then multiply each number by an integer to obtain all whole numbers. So I know it's a little bit wordy, but it'll make sense once we start doing a practice problem. So if I was looking at this problem right here, adipic acid contains 49.32% carbon, 43.84% oxygen, and 6.85% hydrogen. Since we are assuming that all of these problems are out of 100 grams, realistically, if we have 100% of the substance or of the compound or molecule, all of the percentages should add up to 100%. So we can change these percentages to grams. So instead of 49.32% of carbon, we really have 49.32 grams of carbon. 43.84% of oxygen is now grams of oxygen. And same thing, 6.85% of hydrogen is now grams of hydrogen. And so step 1 is to convert these to moles. And you guys already should know how to do this. It's our simple mole conversion. I convert to moles, so I want 1 mole of carbon at the top. And I want to get rid of grams, so I'm going to put grams of carbon on the bottom. And this we pull from the periodic table. This is our molar mass, grams per mole. Okay, so 12.01 for carbon. Remember that when we pull oxygen off, we usually use its diatomic form. When we're using empirical and molecular formula, we just pull one atom. We do not make it diatomic. Okay, so 16 for oxygen, which means we use 1.01 grams for hydrogen as well. And so we're converting all of them to moles. Grams are going to cancel out for all of these. And so then we plug it in our calculator. We get 4.107 moles for carbon, 6.78 moles for hydrogen, and 2.74 moles for oxygen. Do not majorly round until the end. I usually say about 2 to 3 decimal places will keep you from any major rounding issues. So now that I have everything converted to moles, I am going to find the smallest mole value, and I am going to find out the ratios of each of these to that smallest value. Because remember, empirical formula is the smallest value, and remember, we are looking for the empirical formula for this particular problem. Okay? So I see 2.74 is the smallest amount, so I'm going to take each of these and divide it by 2.74 moles. And so the unit moles will actually cancel out, and we are looking at just the ratio of each of these. So I have 4.107 divided by 2.74. I get 1.50. Hydrogen, I plug this in and I get 2.47. And then, of course, 2.74 divided by 2.74 is just 1. So these are technically our ratios for each element. This is what our subscripts would be. However, remember, our subscripts have to be whole numbers. So when we run into a situation where we get a 0.5 or close to a 0.5, we are going to have to make it a whole number. And to make 0.5 a whole number, we multiply it by 2. And what we do to one, we must do to all. So when we do this, we get 3, and this will come to 5, and so you can round after this, and 2. So this is our ratio. For every 3 atoms of carbon, I have 5 atoms of hydrogen and 2 atoms of oxygen. So I will write my formula now. C with a subscript of 3, H with a subscript of 5, excuse that bell, and oxygen with a subscript of 2. So this is my empirical formula. It is my final but yet simplest version of these elements coming together in this specific amount. Okay? So with that in mind, you can do any problem that is given to you this way. So here are some examples that you can pause the video and use to help you. Remember, we just changed percentages to grams. Now, if it gives you grams already, you don't have to change anything. You just proceed like normal to change it to moles, divide it by the smallest mole value, and then compare the ratios and set up the compounds. Okay, these down here kind of work the same way. Takes a little bit more algebra to work with as far as the decomposition goes. So I have 2.68 grams of silver oxide, and it's decomposed, and you get silver remaining. So of course you're going to have to find out how much oxygen was present for this as well. And with this problem, it is a little bit more difficult. I will add another video for that later. Okay, but let's move on to molecular formula. So when I'm looking at molecular formula, I build off of my empirical formula. I have to have my empirical formula there because that is the simplest version of my molecular formula. So when I'm looking at molecular formula, it will give you something similar to the way this reads. The empirical formula for adipic acid is C3H5O2, which we just solved for empirical formula. The molecular mass of adipic acid is 146. Okay? So, what is the molecular formula of adipic acid? They have to give you another molecular mass, and then we can use our empirical formula from there. The first thing you're going to do is you are going to find the formula mass of our empirical formula. So that's 3 times carbon's mass plus 5 times hydrogen's mass plus 2 times oxygen's mass. And so when we plug that in our calculator, we get 73.08 grams. And that's like it says in your notes right here. So once we find our mass, we are going to take the molecular mass they gave us, which is 146 grams per mole, and we are going to divide it by the mass of our empirical formula, which is also represented by grams per mole as well. Remember, formula mass and molar mass are kind of interchangeable because anything we pull for the formula mass is equivalent to 1 mole. Okay, so our units are going to cancel out, and when we plug this in our calculator, we get 2. Okay, and so what this 2 means for our molecular mass, or our molecular formula, sorry, is we multiply our empirical formula subscripts by 2 to get our molecular formula. So I'm going to take C3H5O2, which is our empirical formula, and I'm going to multiply everything by 2. So we FOIL it out. 3 times 2 is C6. 2 times 5 is H10, and 2 times 2 is O4. This would be our molecular formula. Very simple. You just need the empirical formula and be able to add up the mass and divide the answer that's given to you by the answer or the formula mass that you solved for, and then multiply your subscripts by your answer. Okay, usually students will stop here. Make sure you always multiply your original subscripts to get your final answer. And so, of course, we have some more practice with that. This section right here has molecular formula problems. For the most part, it gives you the empirical formula. So here and here, it gives you your molecular formula. 15, 16, and 17 actually has you solve for empirical formulas first, and then has you solve for the molecular formula. So that's adding both techniques together, which is normally what you will have to do. Okay, so hopefully you'll use this additional practice, and I will add the answer keys to Google Classroom once we are done going over this in class.